Welcome, everyone, to our deep dive into the fascinating world of morphine and its structural activity relationships.
Morphine, a name synonymous with pain relief. But what exactly makes this molecule so effective? How does its structure influence its activity in the body? And what have scientists discovered over the years that helps us better understand and utilize this remarkable compound? We'll examine the functional groups, stereochemistry, and molecular interactions that give morphine its unique properties. From the phenolic hydroxyl group to the tertiary amine, each part of the molecule plays a crucial role in its pharmacological effects.
We'll also explore how morphine interacts with the body's opioid receptors, leading to its analgesic and euphoric effects. Understanding these interactions is key to developing new and improved pain relief medications. So, join us as we unravel the mysteries of morphine's structure and discover how this ancient molecule continues to shape modern medicine. Don't forget to like, subscribe, and hit the bell icon to stay updated with all our latest videos. Let's get started. We're diving into the fascinating world of morphine's chemical structure. We'll be breaking down the molecule ring by ring, from A to E, and exploring how each part contributes to its powerful effects. Morphine is a complex molecule with a unique structure that's key to its function. Understanding how to number its rings is essential for grasping its chemical behavior and pharmacological properties. So, let's get started with ring A, the benzene ring, and work our way through to ring E, the dihydrofuran ring. Starting with ring A, the benzene ring. The mnemonic for numbering this ring is cyclohexane adjacent. Begin numbering with the carbon adjacent to the fused ring B as carbon 1. Then, number the carbons sequentially around the ring. Then, number the carbons sequentially around the ring, counterclockwise. Next, we move to ring C, the cyclohexene ring. Remember this with double bond defines. The double bond between carbons 7 and 8 helps to establish the starting point. Continue numbering sequentially around the ring. Note that we start ring C with carbon 5, as we proceed around the cyclohexane ring. Next, we move to ring B, the cyclohexane ring. The mnemonic here is cyclohexane continues. Continue numbering from the benzene ring. Note that we start ring B with carbon 9 as we proceed around the cyclohexane ring. Onto ring D, the piperidine ring. This ring includes the all-important nitrogen atom, part of the tertiary amine group. This nitrogen is key to morphine's interaction with opioid receptors. We continue our numbering from the cyclohexene ring to the piperidine ring, following the molecule's complex dance. Finally, we reach ring E, the dihydrofuran ring. The mnemonic to remember is end with ether. This ring completes the morphine molecule's structure. Continue the numbering sequence from the piperidine ring to the dihydrofuran ring. Let's delve into the very heart of morphine's magical potency, ring A. Ring A, an aromatic benzene ring crowned with a phenolic hydroxyl group at position 3, is not just a structural element, it's the key that unlocks morphine's powerful effects on the mu-opioid receptors in our brains. The phenolic hydroxyl group acts like a crucial handshake between morphine and the opioid receptor. This hydroxyl group forms strong hydrogen bonds with specific amino acids in the receptor's binding site. Imagine the hydrogen atom from the hydroxyl group reaching out and connecting with an electron-rich partner, like oxygen or nitrogen atoms, nestled within the receptor. This bond isn't just a casual greeting, it significantly enhances morphine's binding affinity, amplifying its analgesic prowess. The benzene ring of ring A isn't just sitting there, it's actively engaging in a fascinating dance called pi-pi stacking with aromatic residues like phenylalanine or tyrosine within the receptor. Picture the swirling clouds of pi electrons overlapping, creating a stable and specific connection. This interaction further cements the morphine receptor complex, ensuring that the binding is both strong and precisely targeted. Morphine's benzene ring brings a hydrophobic character to the table. It interacts seamlessly with the hydrophobic regions of the receptor, think of amino acids like leucine or isoleucine. This nonpolar attraction helps snugly position morphine within the receptor's binding pocket, setting the stage for effective activation and the resultant pain relief. Even the weakest forces play a vital role. The close proximity of ring A to various parts of the receptor allows for van der Waals interactions, those subtle, short-range forces arising from fleeting electrical charges. Individually, they are gentle whispers, but collectively, they contribute significantly to the overall binding strength and specificity. Focusing on how subtle modifications to ring A of morphine can lead to astonishingly different compounds with unique effects. Buckle up as we dive deep into the molecular maze. Methylation, morphine becomes codeine. By swapping out the hydroxyl group, OH, at position 3 with a methoxy group, ARC, morphine undergoes a magical transformation into codeine. Increased lipophilicity, this tiny tweak boosts codeine's ability to dissolve in fats, allowing it to slip more easily across the blood-brain barrier. Decreased hydrogen bonding, the methoxy group doesn't bond quite as snugly with opioid receptors, slightly dialing down its binding affinity. Reduced analgesic potency, codeine packs about 10% of morphine's punch when it comes to pain relief, but it's a superstar in suppressing coughs. Next up, acetylation, the birth of heroin. When both hydroxyl groups at positions 3 and 6 are adorned with acetyl groups, OCOG, we get heroin, also known as diacetylmorphine. Greatly increased lipophilicity, heroin's enhanced fat solubility lets it rocket through the blood-brain barrier at lightning speed. Third stop, removal of the hydroxyl group, dihydromorphine emerges. By simply removing the hydroxyl group, OH, at position 3, morphine transforms into dihydromorphine. Altered binding, without the hydroxyl group, the way the molecule interacts with opioid receptors shifts, changing its binding dynamics. Variable analgesic potency, the pain-relieving effects can fluctuate, sometimes matching morphine, other times not, depending on other structural nuances. Fourth destination, bulky substituents, size matters. Introducing larger groups at position 3 brings about significant changes. Steric hindrance, those bulky additions can get in the way, literally blocking the molecule from fitting snugly into the opioid receptor. Decreased receptor affinity, with a poor fit, binding affinity drops, and so does effectiveness. Reduced potency, the result is a compound that's less effective at relieving pain. Fifth journey, halogenation, electrifying changes. Swapping the hydroxyl group with halogens like fluorine, F, or chlorine, Cl, leads to intriguing outcomes. Changed electronic properties, halogens tweak the electron distribution within the molecule, altering how it interacts with receptors. Variable impact on potency, depending on the specific halogen, the compound might become more or less potent. Final stop, introducing other functional groups, meet folcodine. By adding a morpholino group at position 3, we create folcodine. Different therapeutic use, folcodine isn't about pain relief, it's a champion cough suppressant, shining in its antitussive role. Altered receptor interaction, the new group changes how the molecule engages with receptors, shifting its effects. Structural support, provides rigidity and maintains the conformation necessary for optimal binding to the mu-opioid receptor. Alignment of functional groups ensures that key functional groups, such as the phenolic hydroxyl group on ring A and the tertiary amine on ring D, are correctly positioned for receptor interaction. We'll be discussing the 14 and 6 hydroxylation of oxymorphone and how these modifications impact its pharmacological properties. Let's begin by understanding what hydroxylation entails. Hydroxylation is a chemical process in which a hydrogen atom, H, in a compound is replaced by a hydroxyl group, OH. This modification can significantly impact the biological activity of the compound. Oxymorphone is a potent opioid analgesic. When it undergoes hydroxylation at the 14th and 6th positions, several changes occur in its pharmacological profile. One of the primary effects of 14 and 6 hydroxylation is the enhancement of oxymorphone's analgesic potency. This means the modified compound can provide greater pain relief at lower doses compared to the unmodified version. Additionally, these hydroxyl modifications increase oxymorphone's binding affinity to opioid receptors. Higher binding affinity allows the compound to more effectively interact with its target receptors, resulting in stronger and more sustained analgesic effects. Lastly, hydroxylation alters the pharmacokinetics of oxymorphone. This includes changes in the compound's absorption, distribution, metabolism, and excretion. These alterations can affect how the drug is processed in the body, potentially leading to differences in onset of action and duration of effect. Thank you for joining us for part 1 of our lecture on the modifications of morphine's ring structures and their pharmacological implications. We hope you found the content both informative and engaging. Now, to help reinforce your understanding, let's shift gears and dive into the question and answer section. This will give you an opportunity to test your knowledge and ensure you're grasping the key concepts covered so far.